Hi everyone, this is Dr. Manjula Sri, professor in the Department of Electronics and Instrumentation Engineering. Uh, Today's topic in computer organization design, I'll be discussing the basic computers instruction set. Before going to the instruction set, let us see what is the instruction format of the basic computer. So mostly the basic computers instruction format is into two parts. So one part contains the opcode, the other part contains the address. As we already discussed, like it is of 16 bits, 0 to 16. So out of these, even in the earlier example of addressing mode, we have seen that the most significant bit is meant for addressing mode. It will mention a 0 or 1. We represent that as I. So addressing mode. Then we have the memory capacity of 4096 for the basic computer. So which requires a 12-bit addresses. So the address space requires 12 bits. So from the least significant bit, we leave 12 bits meant for address. So the least significant 12 bits are meant for address and will be left only with the 3 bits, and those 3 bits are meant for the opcode. This is the format of the basic computer. But when we are coming to the what are all different instructions in the basic computer, we'll be referring them as register reference instructions, memory reference instructions, and input output instructions. So we categorize all the instructions as three types. So as the name mentions, like the memory reference instructions means the operand is available in the memory, and here all the 12 bits are meant for memory address. So whenever we write any instruction like add or sub or and or, so whatever is a operation that we write under opcode, so with which operand it has to perform will be mentioned in the least significant 12 bits. So these are said to be the memory reference instructions. So the memory reference instructions will be referring to memory location to fetch an operand. Then the other type of register reference instructions. Register reference instructions will be associated with processor registers. Then input output instructions are associated with input and output registers. And in these two registers, how the format is defined is with 3 bits of the opcode, we'll get 8 combinations, right? With 3 bits, we'll get 8 combinations. Those combinations are nothing but from 000 to 111, right? But if you use all the 8 for the memory reference instructions, how do we distinguish? How does the processor distinguish the other type of instructions? So for that purpose, the memory reference instructions will be making use of only 7 combinations, 000 to 110. So it uses only 7 combinations, or else it has only 7 instructions which we can use as with the direct addressing as well as indirect addressing. And the 8th combination in the opcode section with 3 ones, if I is 0, that is understood as a memory reference instruction. If I is 1, that is referred as input output instruction. So with opcode bits, 12, 13, 14 bits as 111. In these two cases, these two are same. If I is 0, they are register reference instructions. If I is 1, they are input output instructions. And we will have 12 bits each, right? So these 12 bits will be using to represent one out of the 12 instructions. There are about 12 instructions under this, under register reference instructions. So one bit is made one for a particular instruction. So like that we'll have 12 combinations. And in input output operations, we have not those many instructions, but we have few instructions mentioned with some code. So we'll see in detail what are those, at least what do they do, because the basic computer is designed for particular functions. So this is the set of basic computers instructions which we'll be calling as a instruction set. So if you look at the table consists of some symbol which is nothing but the mnemonic. We'll be calling this symbol as a mnemonic. Then hexadecimal code followed by what each is doing. So if you look at these three are the three categories. 0002 110 is nothing but 0 to 6. So if you observe here, we have 0 to 6 here with I bit as 0. So most significant bit as 0 will get this. If a most significant bit is 1, we'll get 1002 1110. So this is nothing but 8 to this is E. So these instructions will be having this code for the operand opcode, which will be mentioning. It's an AND instruction, add instruction, load accumulator, store accumulator, branch unconditionally, branch and save the return address, increment and skip if 0. Like these are meant for performing certain operations, certain tasks if you write as a program. Okay. So once we get the operands, when we write AND, one of the operand will keep in accumulator and other one we write as a memory reference instruction, so that when we write this, the content whose address is mentioned here in the instruction will be added to the contents of accumulator. So that is how it will be performing AND add operation also. Similarly, load accumulator means loading the accumulator with the contents of particular memory location. Store accumulator means contents of the accumulator will be stored in the location mentioned in the address in the instruction. The contents of accumulator will be stored in the location whose address is mentioned in the instruction. Then branch unconditionally, usually a jump instruction. Usually we need to jump from one location to the other location based on certain condition or unconditionally. So in that case, we will be making use of this instruction. Then branch and save return address. Usually whenever the control goes to some other location, what is the status of the program it has executed up to that location will be saved, that return address. So usually whenever it has to branch to a particular X location, after executing a subprogram there, so it has to come back and execute the remaining program in the main program. So usually this happens when a subroutine is called or an interrupt occurs. Then what happens is, from the main program, whenever it has to take a branch, it goes in case of interrupt or a branch instruction, and from there it will be executing that instruction, and at the end there will be a return instruction which will come back to this location. How does the processor know that this is the return instruction, return address? So for that purpose, the return address should be saved. That is what is meant by branch and save return address. Similarly, sometimes we have to count for certain programs, like if you increment, if it is not going to be 0, then skip. Like if we are go on counting some 10 numbers I have to count, then what I do is some number, if I add 10, it results in 0. Like for FF, if we add 1, it results in 001. Okay, if I have to count 2 numbers, I will be making FE, FC, F0. If I want to count 9 numbers, if I want to count 15 numbers, then I will be putting 0, F0. Then I will be go on incrementing that register and skipping if it is not 0. So what happens is that operation will be repeated for 15 times because it is hexadecimal number from F0 to FF. Then after FF is reached, if I add one more number, once again if I increment is nothing but adding 1. So if I increment once again, then this becomes 0. Then it will be stopping the process. So this is what is meant by ISZ, increment and skip if 0. We of course will be further discussing in the next lectures also. Then coming to the second group of instructions, which are the uh, register reference instructions. If you observe the full form for this, the opcode has been defined as making 1 bit at a time in the remaining 12 bits address field. Clear AC, this is meant with accumulator. Clear AC is nothing but making accumulator contents 0. Then clear E. In addition, which I have not shown in the diagram, but in the basic computers, there are few flag registers which are said to be a single bit flip-flops. E is for extra bit, like we have carry flag and all in the nowadays systems. So whenever an addition is performed, that carry will be going into the extra flag. That E is meant for that extra flag. Then complement accumulator. AC is meant for accumulator. And complement E, complement extra bit flag. Circulate write accumulator and E. So this is like accumulator will also be having another flip-flop E. This is accumulator and an extra bit E. So whenever we are performing additions, if there is a carry, that carry will be coming over here. Almost like a carry flag. And the other instructions are also associated with the accumulator and the E flag. If you look at the other next two instructions, circulate right, AC and E. The CIR, CIL are meant for circulate right, circulate left along with the E. So usually these operations are meant for performing multiplication by 2 or division by 2 when we are performing shifting right or shifting left. Then in that case, we also need to consider the extra bit. In that case, we will be making use of these instructions. Then incrementing accumulator. See, if you observe, none of these instructions are having any memory location. They are all mentioning a register, either accumulator or E flags in the instructions we have seen so far. Then SPA is meant for skip next instruction if accumulator is positive. How does accumulator is positive or negative is mentioned is the most significant bit of accumulator. Most significant bit usually will be calling as MSB, right? The most significant bit will consider as sign bit. If it is 1, it is negative. If it is 0, it is positive. So the MSB we consider if it is 1, it is negative. If it is 0, it is the positive number. In that way, we will be distinguishing the signed numbers and we'll be making use of the sign instructions also, SPA and SNA. Skip next instruction if accumulator is positive. Skip next instruction if accumulator is negative. That is the meaning. Skip next instruction if accumulator is 0. Accumulator contents are 0. In that case, it will be skipping the next instruction and jumps to the next instruction. That is the meaning of skipping. Usually, the order of execution of any program is instruction after the instruction in the order of their how they have written. So when they are skip means the instead of executing the next instruction, the control will be going to the next instruction. That is what I mean by skip. Similarly, skip next instruction if E is 0. If extra bit is, if there is no carry, skip. And the other thing is, if there is no carry, skip. If the instruction is not satisfied, it will not skip and it will execute the next instruction. In all these 4 instructions, that is the case. And the last one, if you look at, is a halt computer. Actually, this is a instruction which will be controlling the processor. Okay, the CPU will stop executing. Then coming to the third group of instructions are INP is input a character to accumulator. So from the input device, a character will be inputted to the CPU register. Similarly, output character from AC. So through output through accumulator, output register will be sending data to the output device. So it will be sending a character from accumulator. In the same way as we have carry flag, we also have output flag and interrupt flags. Input flag or output flag usually physically they are same. The same flag will be used as input when it is performing some input operations. and the same flag is used as output flag whenever it is performing the output operation. So the instructions that are associated are skip on input flag, skip on output flag. Skip on means avoid executing next instruction and go to the next instruction. That is the meaning of skip. Okay, everywhere it is the same. Then another two instructions are interrupt based. Like there is another flag in addition to E, IO, there is an interrupt flag available. Unless otherwise interrupt flag is set, interrupts will not be entertained. Interrupt is nothing but usually a program is being executed, some other device may interrupt the process, and what the processor has to do is it has to attend that interrupt and answer that, and then it has to go back to the normal program. Something like I am reading the book, somebody knocked the door. So what I do? I stop reading, go open the door, answer that whatever query is there, then come back and continue reading. So that is interrupt. Same is the case when we are reading, somebody calls, when you are driving, somebody calls. These are interrupts. So interrupting the main sequence, main program. So to enable or disable, there is the interrupt flag. There is another flag available in the basic computer which will be facilitating the interrupt or disabling interrupt. So if interrupt flag is disabled, the meaning is that whoever is interrupting, whatever device is interrupting, processor will not take care of that. It will be executing its normal program. Whatever program it is executing, that will be being executed. If interrupt flag is enabled, in that case, if an interrupt occurs, interrupt may be like from the keyboard an interrupt comes while it is executing some other program. So in that case, like whenever an interrupt comes, the processor has to stop whatever it was executing. It has to answer. I also have shown similar thing here. It has to answer that program, and after completing that, it has to come back and continue. How this interrupt is answered is every device, whichever is interrupting, will have its own interrupt service routine. It will have its own program in order to answer whatever it has to do. So that program would be executed after completing that interrupt service subroutine, which in short we call as ISS. That will, once the interrupt service subroutine is completed, it will be ended with a return instruction, which will be taking the control back to the main program. 3:24 p.m. So in that way, the control will be coming back to the main program. So this is how the basic computers operations are defined and the respective instructions are defined for the basic computer. So this is how instruction set point of view or instruction set architecture of the CPU it is called. For any computer, like in order to complete its instruction set, in order to see that its instruction set is complete, it has to perform certain tasks. So it has to fulfill certain basic tasks, like it should have certain categories of instructions. So mostly the basic computer architecture has been, the basic computer's instruction set architecture has been followed by the next advanced processors also. So like the instruction set completeness is possible with a minimum of 4 kinds of instructions. So these 4 instruction types are functional instructions like arithmetic, logic, shift instructions, shift and rotate instructions. So these are the examples, like add we have seen, complement accumulator we have seen, increment we have seen, addition, all these come under addition. Complementing is once complementing, changing all ones to zero, zeros to 1 is complementing. Circulating right, circulating left, all these come under this category. Then transfer instructions or data transfer operations. We'll have data transfer set of instructions where it will be performing transfers between the main memory and the CPU registers. and also between input output devices and the memory input output to the CPU registers. Then a third category is the control instructions, which will be changing the sequence of the program and the control. So when the sequence changes, the control will also be changing. The sequence changes to an instruction which may halt the program. So that will be controlling the program. Then the input output instructions will be meant for receiving some input data to the processor and sending some data to be displayed to the output. So these four categories are required for any computer system, and only with these types of instructions are available, then only the instruction set is complete and it is possible to complete certain task. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.